Hi everyone. So I recorded this last Friday or on the weekend or whenever it was, and I realized that for recording terminals and code, the screen resolution wasn't good enough, so I'm doing it again. But this is fine because I've thought of a few extra things to add to it. So essentially, what I want to do in this video is I'm going to break down a bit the FreeRTOS sort of demo code because I think for some of you, it's going to be a bit too much, sort of jumping in so in depth. There'll be two of them that I'm going to record today. The first one, I'll be going over the branch that you'd find on the GitHub called clean. And essentially, what this branch is, it's a minimal implementation of, well, not minimal, but it's a very sparse demo code. So it's got one task doing not much at all. Whereas the main, like the master branch's demo, main.c is, we've tried to fill it with pretty much all the features, and so the file's huge, and for a lot of you it's going to be very overwhelming. So I'm just going to go through this now. So if we look at my screen, I'm on the repository, and if we look at the branches, just so you know what I'm looking at, there are all these active branches where I'm doing certain things on and whatnot, but essentially we're looking at this clean branch here. So if you forked the repository in the last week, you should have it. If not, you can look at, what can you Google, updating fork from upstream, I guess. Maybe I've probably done this in the past. There might be how you can do, essentially you have to set my fork as a remote, because we talked about in the Git tutorial, have these different remotes. So you have your origin remote, which is your repository really. Wow, my internet's just not having it. And then you can set upstream as a remote, and you can essentially merge changes or get changes. I might do a bit of a tutorial on how to do this when my internet decides it wants to start working. Or maybe it's just DuckDuckGo. So anyway, we'll do this now quickly. Updating fork from upstream. Oops. So syncing a fork, keeping a fork up to date. That sounds good. So be warned that when you do this, for instance, if you want to merge my changes on like master into yours, you'll get conflicts with the code that you've added, for instance. But otherwise, doing this will get you can get the clean branch if you don't have it in your fork already. So you need to add the remote. So here you go git remote add upstream. This is the name. So usually upstream is a word used for, well, it kind of makes sense, upstream. So you have a fork of my work, so you're downstream, and mine's like the original. So normally in computer science, this is called the upstream. And then in here, you would put my repository. So this guy here, this, without the clean, essentially just the link you get from here. You'd put that in, and then you can fetch it, and you can pull upstream clean. And so you'd pull the clean branch to your fork. If you don't have the clean branch. But now that we've got it, this is it, and I'm pretty much just going to sit and work in the in Vim to go through the code a bit and just show how it runs. So I'll get a build window open and move you over, make you a bit small maybe. So if we look here, we'll go through. Hopefully my keyboard's not too loud. I don't have a good microphone at the moment, so I'm hoping that the audio quality is okay. But essentially what we're going to be looking through is, this is the main. So this is obviously where your code starts and where everything is, everything for this demo is contained. Now, going from the top down, really, these are the standard libraries and things that you shouldn't really need to worry about if you're looking for certain print functions, math functions, whatnot. You'll need to look into like the standard C libraries, but that's sort of up to you, and that's just basic C. But where we sort of start to look for the course is we'll see this file. Now this file I'll explain in a minute. These are the FreeRTOS sources. So these are needed to be included for getting queues, semaphores, and tasks. Like all the different FreeRTOS APIs have separate files for them. So you can include and exclude the functionalities that you need. Now before you include something, you need to include freertos.h. If you don't do this, like for instance, if I was also to put tasks include here, this will throw a compile error, right? So now we have these 5 files here. Now these are essentially the little like libraries that I wrote for the emulator. And I'll go through some of them now. Some of them we don't really need, or you wouldn't really need, like there's the sound API and the util API. Now, sound is a functionality that I sort of played around with a bit, and the Pong demo does use it, and it's up to you if you want to implement it. I'm not really requiring sound necessarily for the project because on the embedded systems we never did it, so it's sort of, it doesn't really fit the standard requirements for ESPL. But these three here are quite, or not really, like for instance, TUM ball is not important for you as it's just sort of like a really template, quick, hacky implementation that I did of collision detection using a ball and a wall. But unless you want to directly use it, but it's definitely probably got some code in there that you can pull inspiration from when it comes to the project and implementing a game. I'm by no means a game engine developer, and so I wouldn't say that the code that I wrote is by any means like good. But it does the trick, and it definitely shows some sort of basic concepts of object clashing, and also just the one thing you can take from the files though is structuring of the code, because regardless of the application is good. I mean, I'm a Linux guy, and so when I write a driver, it's got a very similar structure in like how I structure my objects and blah blah blah. Anyway. Draw an event. This is where most of the stuff that you use comes from. So the event files are handling all of the mouse input and the button input, essentially, which is all of the events you'll be dealing with. And draw handles all of the drawing to the screen. But we'll see this in a minute now, right? And this here, for this example, is not directly required. This is mostly for the main, like the master branches main, where we do the async IO, which is essentially communications. This is going to come into the project, and I'll probably touch on the communications when I do in a minute. I'll do another one of these videos for the master branch, and then later towards the project, I might do a more in-depth explanation of the comms, because it's definitely the most complex part of the emulator, and I think it requires its own explanation, very slowly broken down. So now I'm just going to walk through the files. So where is my window? Yep. So if we go down to we'll go down to my main, right? Because this is where it all starts, and we'll start breaking down what it is. Now, in the main, you'll see a few lines. You've got this line. This is just some printing, and essentially down until here. Now this code is, the first line is getting the binaries folders, like the binaries location on your computer. And this is required because I need to, when I'm initting the drawing library, the fonts that I've loaded for the TTF or TFF, whatever it is, STL font stuff, they're hard coded in the resources folder, I think it is. And so to get that folder, I need the binaries for that. Either way, all you need to know is that whenever you're doing your code, just leave this stuff in there. It's just sort of stuff that you don't need to worry about, as well as the init stuff, init events, init audio. Now, what these are there for is, as I explained in the semaphores lecture or the FreeRTOS lecture, that the semaphore handles that I'm embedding in all my structures are not initialized, they're just handles. And so before they're initialized, you can't use the semaphore. And what these functions do in the most part is just initialize these things. So if we look at, for instance, TUM events, so if we go into him and look at the source file, well, I don't need you right now. So if we look at init events here, we'll see that it's calling init mouse, and init mouse, wherever he is just initializing the mutex used to lock the mouse's data structure, right? So the data structure you can see up here. So it is where the actual X and the Y of the mouse is stored, and they're locked because there's a thread to update it, and then obviously you can pull in your calls to get the values. And so this needs to be locked in the similar way or in the exact same way I was explaining in the FreeRTOS lecture when I was touching on mutexes, right? Because this is a shared resource, we want to use a mutex, not a semaphore, because we need to make sure that we don't have priority inversion and all of this stuff. But anyway, so if we go back to main, this is event cell, main, we'll see a very similar thing here. We've got another mutex created, and I'll explain in a minute as I go through the task loop why I have this mutex, and hopefully it should become quite clear to you with this whole resource locking thing. So down here we have the one call to the create tasks. Now in this demo, I only have a single task running. So by sort of normal embedded system standards, this is just like a bare metal. We have one loop that runs really. So the scheduler doesn't actually do much in this case since it's just got one task. But it's a very thinned down example, and it's probably a very clear way of showing you how a task runs, like a single task. So the call to the FreeRTOS API for creating the task is this guy here. And I've simply just wrapped it inside of an if statement, because if we go and look at FreeRTOS API, now there'll be a file, now DuckDuckGo wants to work again. This guy here, and so we look at task creation. So this website will be the one that you should pretty much refer to for any FreeRTOS stuff. I haven't written documentation for it. It's all the standard source files, so that all the FreeRTOS documentation you find online is valid. Now we have this. This is our call. So the first argument of this is hopefully task create. So we have first parameter, task code. Now this is a pointer to the task entry function. So if you don't know what function pointers are, maybe do a bit of a Google and read up on them. As you can imagine, everything in C is a memory address, and just as you can have a pointer to a function, you can have a pointer to the code, like the entry point of a function. Just like you can have a pointer to a variable, you can have a pointer to the entry of a function, like the entry point of a function, meaning that you can actually link, like you can have function pointers or in like a structure or something, and then you can dynamically allocate the actual function that it should call. In a nutshell, that's what a function pointer is. But so I imagine at some point in this task create structure, it's creating some sort of a task header structure, some sort of a metadata structure, and in there it's obviously saving a pointer to the task itself. Now if you look at this, we need to find out what task function is, because it'll have a certain structure to it. Now the function pointer has to have a certain structure. If this doesn't show us, yes, okay, so you'll see here, implementing a task should have the following structure. Now this function structure is exactly what the function pointer is going to need. You're going to need a void and a void pointer argument, right? So it doesn't return anything because a task should never return, right? And you can pass it in parameters, which we'll see in a second. So essentially you just want to put in as your first argument to task create the function itself. So if we look at my example here and we look where vdemo task is, we'll see that it is this function here, which has this exact structure that we needed, right? So the second argument that we need, where is my, go back. So the second one is a name. So it's just some string. This is used for like kind of bookkeeping stuff. If you can sort of write task managers and whatnot, but by all means you probably won't use this very much. But just put in some name that signifies it. If you get into really in-depth debugging, you can look into the structures, and it's very, very handy to have an ASCII or a human readable name of the task, right? Now we'll get into the stack depth. As I was explaining in the FreeRTOS lecture, tasks have a stack where they push on, do sort of stuff with, essentially have an allocated chunk of memory that they are allowed to use. So when you save the context, this is the stack that's getting saved. Because FreeRTOS is an embedded systems operating system, generally, it works in a way that you can allocate or you can define how large this stack should be. Unlike most computers, this stack can dynamically grow and whatnot, and because we have gigabytes of RAM, but on these sort of embedded systems, you definitely need to have more control over it. Now there are two ways of creating a task or a stack. You can either do it dynamically or statically. Statically meaning that you allocate or you have the actual array of memory allocated and you pass in saying, hey, this is a chunk of memory you should use, or dynamic meaning you just create the task and call it saying we want to stack this large. Usually you just use dynamic. It's easier because it sort of guarantees, I mean, either way you have the same size of memory because you're giving it a fixed stack size bound. So all this, I guess we don't really want to look at this. So all it is we need to give it a size, and I'm pretty sure the size is in words. Yes, the number of words, not bytes. So I think a word, this is pushing my memory, is like 4 bytes. So here we can see we have this generic stack size, which is just a define I have of 2,560 words. Now this is a lot of memory, right? But given that we're an x86 system, I'm not really caring about it. If you were to do this on the STM boards, you'd be dealing with stack sizes of like 10 to 100, maximum like 500 to 1,000, right? So 2,560 is just overkill, but I don't want to be writing demo code that's having stack overflow issues and whatnot. So in this case, the emulator in this semester doesn't really capture this, but now you should just know and understand that why this number is there and what the stack is. So we'll see that we've given it in a size times 2. So essentially this is something like 5,000 words. Null, so what's the next argument? The parameters. Now we saw in here, we have a function pointer. Now, when you save a function pointer into a structure, the general way you have to pass it arguments, meaning that like when the function is called, you actually give it the arguments, is to save the arguments in a separate member of the same objects that stores the function pointer and the arguments, and then some function that's using this object will call the function pointer and pass it the arguments that are saved in the same structure. So if you read up on function pointers, you might come across this. All you need to know is that the arguments that are passed into your function that is running as your task have to be given into the create function as a void pointer. So I'm not passing any function arguments in, so I just have null, which is essentially a null pointer. And then here, the priority. Now we'll see, as I talked about in the FreeRTOS lecture, we have different priorities that we can give to tasks, and it's how the scheduler determines what tasks should run at what points in time. So this here, generic priority, is again just another macro for task idle priority and task idle priority. If we go into the RTOS sources, is just 0, so it's the lowest priority, or it's a special priority. It's essentially when nothing else is able to be run, the idle task runs, because the scheduler itself always has to have some task being run. And how the scheduler actually works is that when there's no other task able to be run, it runs an idle task, which essentially does nothing. So what I'm doing by saying generic priority in this example is I only have one task, so I don't really care about the priority, so I've just given it the idle task priority, meaning it's super unimportant, right? But if we look at, for instance, the include and the FreeRTOS config, this is the file where everything is configured for your kernel, your build sort of thing. You can see there'll be like max priority somewhere. Yes, so here, this guy. So what I've configured in this file is I can say I have a maximum of 10 priorities. So I have priorities 1 through to 10, right? With 10 being the most important and 1 being the least important, right? And then you have this 0, which is underneath 1, which is this idle task. So you don't really need it much or ever, but it's like the default. And I have one task, so I don't really care about the priority. But for you, if you have multiple tasks and you have things that are more important than others, like in a game, you have a frame swapping task that's very important, whereas drawing something is not necessarily as important. You're more focused on keeping your FPS than you are actually making sure that everything's drawn, right? So you'd prioritize swapping the frames over drawing, because you want to, if your drawing is not done in time, it'll just draw to the next frame, but you want to maintain this smooth frame update rate, right? So now that we've seen the priority, this is the next thing passed through. Now go back to, where is it? We'll see that we have here demo task. Now this is the last thing we require, and this is a task handle and a pointer to a task handle. So you have to be very careful of these little asterisks. Depending on how experienced you are with C, I would definitely recommend reading up on pointers if it's something that you're not really too savvy on. I might do a lecture on it because it's generally one of the weak points. And if students aren't comfortable with pointers, they're generally trying to avoid using them, which generally leads to not very elegant code, or code that's very hard to work with. Pointers are great. Pointers are the best thing about C. But we'll see at the top of the file that we have this task handle defined. Static, for those that don't know, means that it's only accessible in this file. It not super required in this situation with my sort of one file project. But it's good practice to put static in front of things that are only used in the one file. And I'll also do a lecture probably next week on, after this FreeRTOS, I don't really have much content left to give because the rest of the course goes about sort of actually getting practical with it. But I generally try and do sort of tutorials every week where I'll look at certain things like state machines or good sort of APIs, how to write them and whatnot. And we'll see in there that when we're doing sort of creating mini APIs, using static becomes very good because it creates very nice binaries like on actual code level, but it also sort of is the same as using public and private when you get to other more high level languages like Java and Python and whatnot, right? But anyway, so we have defined at the top our task handle, and it's initialized. I've just initialized it to null. Now, this is sort of like a defensive programming strategy, which I employ most of the time, and this is that this demo task shouldn't be used before it's initialized, but by initializing it to null, I always have the option to check it first. So I can always say if demo task is null, and then I go to an error because it hasn't been initialized. So this is really important for queues, because a queue's handle, if you don't initialize it, will have some random value in there. So if you check the handle, it might look like it's initialized. When you try and use it, you'll get an error. But if you initialize it to null, you can first check that the queue handle is not null, meaning it's been initialized, and then use the queue. And this will let you to check that you're not going into uninitialized memory and all sorts of stuff like this. But essentially, initializing variables that you are going to initialize to null or 0 is good practice, because then you can then check to see if they're still 0 or null. And if you're trying to use them when they're 0 or null, you know they've not been initialized yet. So just pro tip, anyway, we'll go back. And so this thing is the last thing passed into our function as a pointer. So you need to dereference it with the ampersand to get the memory address of demo task. Now the handle, maybe it talks about it here. No, it doesn't really. So the handle essentially is a reference, or it's the thing you use to reference this task itself. So if you want to pause, or if you want to suspend this task, or resume this task, or destroy this task, you need to have this handle. Because you can't access the task itself. That's done all by the scheduler. But if you want to call one of the FreeRTOS functions that is sort of for task control, you need to be able to reference the task itself by the handle. So usually you'll create a handle for each task, and then you'll keep this handle and use it in the future for starting and stopping and controlling the task. So we'll see here it returns PD pass. So that's exactly what I have in this conditional. I say if not PD pass, meaning it failed, I go to an error. Now I should also sort of go into, this is also separate to FreeRTOS and has nothing to do with FreeRTOS, but just to sort of explain all of the things I'm using in my code. And if you're going to go into the library files, or just in general, a lot of C code has this go-to function, and it's not something that students really have had exposure to and at this point in their studies. It's also took me a while, really, like in my programming career, to get really to use it, and I find it really nice to use. And it's also, if you go into the Linux kernel, it's everywhere, because it leads to really easy to understand code, because I was talking about the code style and whatnot, and code that's well formatted should be able to read really easily. And by doing this sort of style, you can actually, you show your error handling very cleanly and in one block. But anyway, the go-to task, what it essentially does is it jumps to a certain location. And so when I hit this line, it'll actually jump down to error demet, this label here, and it'll start executing. Now labels fall through each other, meaning that when I hit error demo task, I'm going to execute semaphore delete, then I'm going to exit the audio, exit events, exit drawing, and finally return and exit failure. So what I actually look at the structure of my go-tos, I am essentially building up my system, and whenever I hit an error, I jump down to the appropriate error statement and destroy my system, essentially uninitialize everything I've just initialized. It's just good cleanup, and this becomes really important for doing applications that use things that are more than just variables, like if I'm opening sockets or message queues, or something that's actually initialized and created in the kernel, like I have some sort of a dev then if you don't break these down when you exit your code, you might have problems that the next time you try and run your code and you're trying to open a message queue, for instance, with the exact same name, it's going to say, hey, we can't do this. This message queue already exists. And these, you have the problems that these message queues can just become hanging. They're not really attached to a process, and they're really hard to destroy. You can't, you pretty much have to restart your system. And this is annoying. So instead of just exiting your program, you sort of try and break down what you've created. And the go-to is a really easy way of doing this. You just reverse order what you've done. So this is just explaining what this is. I would recommend students to sort of just have a go with them, use them. I find them really nice, and they lead to really easily to follow and clean code. But now we'll go to the main thing of this example, which is the main or the task that I'm creating, this demo task. Now, as we saw in this page here, the task structure is essentially a for loop, right? And so, as I was saying in the RTOS lecture, a task is generally like a non-terminating task. So meaning like a task and not so much just a work packet, should be some sort of a loop that runs indefinitely. And for those that have some experience with like Arduino, like really basic embedded systems, your main function usually just has a while loop in it, and then it runs indefinitely, because embedded systems don't really want to exit. They get turned on and they do one thing forever, right? And so they have this non-exiting loop, and a task is very similar. So if you read this here, this also says that this task shouldn't exit. Like, you shouldn't return your task. If you don't need your task anymore, you use the FreeRTOS API calls for task control to actually delete the task. Like this guy here, like vtask delete with a null pointer, like a null handle will delete the calling task. You can read into this stuff, but you should never return, meaning you should never be able to hit the end of your code. So because of this while loop structure, for instance here, this for loop, you can imagine that the first time this task gets called, it comes through and it'll call anything that happens before this loop just once. So in a way, you can think of the code I have here. This is my task's initialization code. This will get run once, and after that, it'll just run my while loop. So all I'm doing in this example is I'm creating the variables on my stack for this task that I will need in the execution of my task. So in this case, I have a struct time spec, which I'm using to get to time, because as we'll see in a second, this example is doing nothing but getting the real-time clock from the Linux kernel and displaying it on the screen. And so I have a time spec struct that I use when I call the clock get time syscall to get the kernel time. And then I have a string or a character buffer where I'm actually, once I get the time, I format up a string that I then send to the TUM draw backend to draw a string on the screen. And then I have one integer here, which I'll show in a minute, that I'm using to store my string's length in pixels so that I can align it nicely and make it pretty. But anyway, so if we expand the code, we'll see this one call here as well that's getting called in the initialization of my code. Now this is also sort of a bit more involved and definitely beyond the scope of this course, but you should know that what this call does, and you should know where to place it, because you're going to need to place it. How the back end of the libraries that we wrote work is that they're running on STL, which is a very simple, basic C graphics library that leverages OpenGL for hardware support and for drawing, right? So like most applications on most systems, OpenGL is important. But what the problem is that the STL is not implicitly multi-threading, and because we're running a multi-threaded application, we need to bind the application that's drawing to the screen to the OpenGL context. Now explaining what this is, I'm probably not the best person to ask, because I'm also not a guy who really deals with graphics much, but also it's definitely beyond the scope of this course. But all you need to know is that only one task can call the drawing function that draws to the screen, which in our case for our library is this draw update screen. So wherever this draw update screen is located in your code, you should also have this bind drawing call, which binds the OpenGL context to that task, like that thread on your system. So in this case, we only have the one task that's drawing to the screen, and so we bind it here. I think in the main, if we look in the large main, like the full main for the master branch, like the large demo, we're binding it to our frame swapper task, right? So if we look at source main and bind drawing, yes, so we have this frame swapper task, which I'll see explain in the next demo, but it's doing this the update screen, and therefore it needs to have the context bound to it, right? So just be aware of this. You can follow the sort of example structure of this, the master branches main, to get this like buffer swapping stuff going on, but that's just the explanation for that one line. Now I don't actually need this anymore. So going down further now, how I should probably open quickly the what is it? It's half.github FreeRTOS Emulator. So this is the just the Doxygen documentation from the file libraries that get automatically uploaded to the GitHub page for the repository. And we want to look at, for instance, fetch events. So we'll go in modules and we want the event API, and then we'll see fetch events. So what this does is it gets all of the SDL, like SDL is this library as I mentioned, and it handles the graphics, but it also handles the input from the keyboard and the mouse. And so how it works is that it stores these events, and then when you poll, or like it stores them in its backend, not in the emulator, and then we call this function and we essentially retrieve all of these events. And so when we want to see if there was a button press, we first need to retrieve these events from the SDL backend. And so in this case, we're getting the button input. And so firstly, we should fetch any input events, to see if any buttons were pressed. So that's what this does. It's a pretty simple function. You can call it as much as you want, really, but you shouldn't need to call it that much. Sort of place it tactically to keep the overhead of polling fetch events to a minimum, right? So that's what that does. And now if we see this function, this one I've written up here. Now, before I get into this, I should probably explain, I initialized in my main this semaphore, which I didn't really explain before. Now, this semaphore, or this mutex, sorry, this mutex is there to lock this button structure that I have in my file. Now, what exactly this button structure is, I'll explain right now. But it has a lock in it, and this lock, of course, needs to get initialized, which I've done in my main. So if we go to buttons, which is up the top somewhere, where are you? Go to the top. We'll see here I have this buttons buffer. So this is my a structure I've created with a lock in it, and so obviously, I mean, it should be sort of apparent that when I put a lock in a structure, this lock locks the structure itself, as I was mentioning in my last lecture. Now I've instantiated this the static, this type def, this buttons buffer t, to create buttons. So buttons is an instance of struct buttons buffer. So it is essentially just a really long array of unsigned characters, and it has a lock. So the lock is there when I want to use it. I take the lock, I use the structure, and I give it back. So if we look into my X button get button input, you'll see I'm locking it, and then I'm using it. In this case, I'm updating it, and then I'm giving it back. And if we look down into the rest of the loop, or the struct here, we'll see here I'm checking to see if a button is being pressed, which I'll explain in a minute. But essentially, I'm now not writing to it, but I'm reading from the structure. And even either doing writing or reading, you still need to like take the lock and return the lock, right? Because if this didn't happen, then you could get clashes, especially if you're using button presses in multiple tasks, which most of you will do in the project or in the exercises. So now that I'll sort of explain what this is doing, but firstly to understand how that works, how it's working, we need to look at what exactly this char array does or purpose it fulfills. Now, the STL backend handles the events, but also it has these scan codes for each button. So each button has some value attached to it that you can, like it'll return an event for a key press, and it'll say 4 was pressed, and you don't literally not the number 4 key, but some number that's referenced by the number 4, and this is called a scan code. And the scan codes are all defined in this header file here. So if we go to it, so I'll find it quickly on my system. I'm pretty sure I looked for it before. It's in user include or something. Here we go. So we'll go to /user include, yes, SCL2, and then STL scan code. And so in this file, you'll see a large enum, which there are some scan code. This is a scan code for A. So A is the letter 4, the number 4, right? And there's a number of them. So if we look for STL num scan codes, we'll see there's 512 of them. There's a maximum number possible, essentially. So if you have an array of this length, you're guaranteed to be able to store all of the possible scan codes. And so why I'm creating an array of this length is I should then, for those of you that don't have any experience with it, quickly explain what a lookup table is. Now, a lookup table is if you had some sort of an array, and each index stores some value for some sort of a reference, right? So in this case, we have all of the keyboard, the letters of like the keys of the keyboard, and we want to, for instance, look up what's the status of A. Now we can either go through and check each object, each index, and be like, is this the key A? Yes, and then you can check its status. But this means you iterate through each individual entry in your array, and so the longer the array, the longer the search time, like the actual computational time of finding the status can be. And so this is a linear time complexity, meaning the larger the array, the larger the time to find it, right? Now, the lookup table gives you a time complexity of 1, meaning regardless of the length of your array, the lookup time is always the same. And because it works in the principle that since we know that the scan code of A is 4, we will then store the status of A in the 4th index. So we use the identifier, which is the scan code of A, as the index, meaning that we can just quickly, like we know exactly where to look in memory to get the status. So it saves us this sort of going through and looking to see if it's the right one and then checking the status. If this doesn't quite make sense, pause this video now and just type into YouTube lookup tables. They're they're really good thing to know. They're like the bread and butter of computer science with quick data access, right? So you need large amounts of memory to store them, so they're not like sometimes the most storage efficient ways of storing data, since as you can see here we have like 300 or 200 indexes that aren't used, so we have 200 bytes in memory that are not getting used, which is super inefficient. But for the trade-off is that we have a time complexity of 1 for accessing the statuses. But because I have this lookup table, which has a max, and I have a maximum possible length, maximum possible scan code of 512, I therefore want to have my lookup table the same length to accommodate for all the possible scan codes that I could get, right? And so, go back, I don't need you. So now we've seen that that's the file which defines all the scan codes, and when we want to access this, the certain index, meaning if we want to look for A, we can use this macro, or you can just use the scan codes themselves. But we'll see that in a second, how that happens. But how the events backend works, if we go to here, the input queue. Now the events backend, or the buttons lookup table, to get a copy of it, to get the most up-to-date statuses, you essentially get an entire copy of this lookup table via a queue. And so you have to, it sort of explains it here, what it is, but what we want to do, as you can see this call here, what I'm doing with this call is I'm saying I want to read from input queue, and a packet size, as I'm explaining in RTOS, the packet size for this queue is the entire lookup table. So I'm saying I want to read from input queue, and I want to put it in my button structure inside the buttons, which is this lookup table char inside char array, right? And I also have a 0 here, meaning it's going to attempt to read it, but if it doesn't read it, it's just going to keep going. And this here is a design decision, as you can imagine. This loop is sort of looking for button presses every loop, and if this loop is running, let's say for like a 50 hertz game, so you're running every 20 milliseconds, if I'm pressing a user input, like left, if I get it this frame or the next frame, it doesn't really impact the gameplay for me as a human being extremely slow compared to a computer. And so by not blocking on this call, I'm trying to say, try and get new buttons. If it's going to take too long, it's probably better for me to just continue with the old button values and then get the new buttons next frame, instead of blocking, for instance, for like 100, 200 milliseconds, which would then maybe freeze the game and really degrade the user experience. And so this is why an example of when you would use like a non-blocking call, because it's not important that we have the most up-to-date button values, because the button values come from a human and we're very slow. So we can just use the button values next frame, for instance, right? And then we can just see here, as I was saying before, we used the button, like the structure, and so we took the lock and we gave the lock back. Now you can see here as well, I've used no blocking time because it's the same principle. Getting new button values for me it would be nice, but if I can't get them straight away, I would prefer to just continue on and get the new values next frame or something, because actually blocking the game on the button input might lead to a bad user experience. And so this should hopefully make sense. But because I have a no blocking time, we need to make sure that we were able to get the semaphore. So if I have, and you'll commonly see this sometimes in FreeRTOS code, if I put in like max delay here, you don't need to have this conditional statement necessarily, because the code will block until the mutex was returned. Like you won't go past this line of code. But if I have no delay here, the code's not going to block on this line and it will continue straight away. So you need to obviously check that if it's successfully if it's continuing because it successfully got the mutex, or if it's continuing because it couldn't get the mutex and it was blocked, right? So you need to put the conditional here to check, hey, yep, okay, my call to semaphore take return PD true, meaning I've obtained the mutex, then I can do my stuff, and then I return my mutex, because if I took it, I need to give it back, right? And so that should hopefully make sense what's happening here. We're getting a new version of the entire lookup table. And then if we go into our code more, you can see here that I'm taking the same lock again. Now this is because the other function comes from the masters branch implementation, and it's really overhead wise, this is not very efficient, because I'm taking a lock, doing something, giving the lock, taking it back straight away again. Now, ideally it's up to you to sort of decide where things should be partitioned, because the one advantage that this does present is that between the X button input, between this give and this take, other tasks have the ability to take the mutex and use it. So you do give it a small window where other tasks can actually obtain the resource. But from an overhead point of view, giving and then taking it back straight away is not very efficient. But this is all a design question, what's better for your application. But as you can see here, we're taking the semaphore and then we're using the buttons lookup table. And in this case, we want to see if Q was pressed, like the quit button. And here I have STL scan code Q, and this is because I was recording this last week. But what we can do here instead is that we can use this macro that I've written above, which might be easier for you to use. Now, I explained a bit like macros and pre-process substitutions and whatnot in the Git tutorial. But what this macro does is that it's like a function call. You have the macro called keycode, and it takes in one argument. In this case, it's called char in the macro. And what it does is that whatever's put into here gets put into here as like a string. And these little hashes are just because you use it to put them together. So the macro knows that this char here is this variable. But what this does is that whatever I put into here ends up STL underscore scan code underscore and then that chunk. So if I was to go in here and I want to put in key code Q, this would generate me the same as this is equivalent to STL scan code Q. All right? So if that makes sense to you. And this scan code is just coming from this STL/STL scan code.h. And so for the most part, you'll be using like pretty much the basic keyboard things and maybe the arrow keys, and you can just go and have a look in that file. Like all the keys on the keyboard are labeled by their actual character. The arrow keys you'll have to look up. It should also be in this header file what they are, but I imagine there'll be something like right underscore arrow or something, right? And so going back to this, we are again not blocking, because if Q has, for us essentially, if Q was pressed and we have to block to get the value, for us it's just better to handle it next frame, because it'll make the process smoother, right? And then here, for instance, if we get Q, we exit. Simple as that. And then we give. Now ideally, we would, for instance, break down our code. So we would use some like go-tos and we would uninitialize the semaphores and blah, 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 blah. But this basic example doesn't create anything that's not going to get automatically cleaned up when the binary gets thrown out of memory, like when this process on the kernel gets killed. So that's what that does. Now we'll get to drawing. Now, so if we go back to this documentation generated, we can see in the modules, also this is pretty much the same as the files. These are all the different files that have been generated. But if we go into drawing, these are all the different functions that I've implemented for the draw library. And if you see here, TUM draw clear, we can find this here somewhere, sets the screen to a solid color. It's essentially like the paint application where you have a little bucket. Now, you give it a color here, and if you go into this file, you'll also see all of these, some defines that I've added for pre-existing colors in the library. Now, they're an RGB, a 24-bit RGB value, meaning like 8 bits R, 8 bits G, and 8 bits B. So you can use whatever you want, get fancy, but some of the basic ones I've added in here. And so you can see I'm using white, which in hex is like F, right? So it's just full max value, 24-bit max val. And how the drawing works is that on a normal embedded system with like with an LCD, you have this principle of swapping buffers. And so it's, how do I explain it? We have essentially the screen, like what you're seeing, like this is the top one, and then you have a buffer that's in the background that you're writing to. So you don't actually directly write to the screen in most applications. You're writing to some background buffer, and then the screen swaps these. So you have time between frames to prepare what's on this guy by doing all sorts of writing and drawing and whatnot. And then when this frame is finished being drawn to in memory, essentially it'll just swap them, usually just by pointing to the other buffer, and it just points back and forth between the two. And it's the same idea in this drawing library, is that it doesn't work necessarily in two solid buffers, but we have a queue of stuff that needs to get done. And so we add to this like sort of queue of stuff to get done, and then when we call update screen, all of this gets drawn to the screen. So we are in a way writing to some background buffer that then gets updated to the screen when we call this draw update screen. So everything that's happened since the last draw update screen is sequential in a queue that's going to get applied to the screen, right? So the first thing that will get applied to the screen is it will clear the entire screen with white. So it's going to get rid of anything that we have on the screen. And then you'll see here that we're going to draw some text onto the screen, so on top of the white, which we'll get into in a second. So that's what the TUM draw does. Now, as I was saying here, this application, and if we go to, where's my, I don't need you, here. Now if we run the application as it is at the moment, it's just counting up and it's putting some blue text on the background, and it's showing the seconds since the epoch. Now the epoch is like some time in the 70s, and essentially it's just the seconds since that time in the 70s. But how I'm getting this time is I'm getting it from the kernel. So if we look at man like clock get time, we'll see that here we can get the real-time clock. So it gets the settable system-wide clock with measurable blah, blah, blah. And how it works is that this is the call. It returns an integer, which is probably just a return value. In general, 0 means no errors. It takes in the clock ID, which is this guy. So these are the different clocks. And then you give it a pointer to a structure where it's going to save the time. It's going to essentially copy the time in, like I was saying, that it's a thread safe way of returning an argument is to copy data and then send the data back. And so in this case, we're getting more than just one return value, so it can't just return the time to us, but instead it'll fill the structure, and after we've called it, we'll know that the structure is populated with the return value. And so in my code at the top, I created my time spec. Now this is not a pointer, but an actual static instance of the structure, which I then pass through as a pointer using the ampersand, like the dereference. And I'm using the Mac, I'm just typing this define clock real time, which is the clock ID. And so once this gets called, I'll then have a structure, this time spec structure, where it has the seconds and the nanoseconds stored in it. And so all I'm interested in is this nanoseconds. And if we look into time t, I think it's usually just an unsigned long or something. I have it here. Yes, it's a long int. So what I'm going to do is I have my clock time now. I've gotten the time, and all I'm interested in is I have this value. And then to print onto the screen, I need to have this stuff formatted into a string, which is saved in some buffer. And as I said before, I created here a char buffer, and this is where I'm going to save my stuff into temporarily as I get ready to draw it to the screen. So that's what I'm doing here with sprintf. Now, if we look at the sprintf, looking at the whole family of these functions, like printf, or printf and fprintf, where are they? Yep, here. So fprintf prints out to standard out, fprintf, and lets you specify the output stream. For those that don't know, 2-second summary of what a stream is. Standard systems like a Linux system have different output streams. For instance, standard out is what gets shown in your terminal. Standard error is also shown on the terminal, but it's generally where error messages are put. But you can also have an output stream into a file, and a file. So if you wanted to essentially write out to a file in C, you open a file and then you pass it into fprintf as the stream, and it will just write into the file. So why we're using sprintf here, so for sprintf, it's writing to the character string that you pass in as the stream. So here, if we look at sprintf, the first argument is a character pointer to a string called str. And so str is then the stream, and sprintf writes into this string. And so that's exactly what we're doing here. We've given it the stream we want to write into, and then we've given it a format string. And so this, or maybe it's explained here what a format string is. Essentially, if you type into Google like printf or something, it'll show you how you format using the percentage signs and all the different sort of identifying characters. But what I'm doing here is I'm writing this string here, and where this percentage LD is, LD standing for long int, the value here is substituted in. And so that's when we run the program, we'll see we have the same format of string, but where this LD is, this value has been substituted in that I'm getting from my clock get time syscall, right? So now after this line of code, we should have this string formatted. Like we'll have a copy of this string formatted like this in memory as a char array, like as a string. And then what we want to do is, as you can see in this example, if I run it again, I have the string centered left to right, and also like top to bottom. And the coordinate system, I'm not sure if I've mentioned this in a lecture, in most graphical applications is the top left-hand corner. So the X obviously goes up as it goes across, and the Y, which is the bit that people get confused about, it doesn't go from the bottom up like you would when you look at a normal graph. It goes from the top left corner down, right? So the 10th pixel is down here, 20th, 30th, whatever, right? And it's the same for any sort of a string. So when you're drawing the string, it has a bounding box, meaning a box around it, and its location is where the top left-hand corner of this bounding box is on the screen. So what I want to do is I need to find out how large this bounding box is, because the text itself is just a string, and depending on the font I'm using, the size of the font, it's going to actually end up being a certain amount of pixels. And so if we look in the documentation, we can see this call here, TUM get text size. Now, TUM get image size, get text size, finds the width and the height of a string's bounding box. So we want to then, because I want to center the text in the middle of the screen, I also need to subtract half of the text's height. And if I want to put it in the center of the screen on the X, I need to also find the length of the string so I can put the string in the middle of the screen and then shift it back half of the text length to put it in the middle of the screen, if that makes sense. And so I don't really necessarily need this TUM gets text size call. I could have just put in some manual coordinates to put it roughly in the middle. But this way I can scale my screen's resolution. The text is always going to land in the middle. So a few things about this call is this function call might confuse a few people, especially the format of this stupid formatting. So I should probably, I'll put him down here, or maybe move him up here. So take him and put him here, and give it a reformat. Maybe it's a bit cleaner to see. So maybe just for demonstration, I'll put him here. There we go. This is easier to read. So this TUM text size, if we look at the documentation, it returns 0 on success. So we'll firstly look at this conditional statement. Now, but the value that I'm storing it in, I want to get the string's width. The height of it, you'll see in a second, I'm just using the font's height because I know this is fixed. Like the string's length can vary, but the height of it's always going to be the same because I'm always using the same font. But I want to store the width in this variable that I created up here. So this is not an integer pointer, it's just a variable, an integer that I'll then pass in as a pointer, and it'll be populated with the width as this function executes, right? But the thing I want to know is that I only want to draw my text if this function returns successfully, because if it didn't return successfully, there could be anything in this value, and it might draw my string off the screen, or it could maybe, like in some cases with certain functions, it will crash the system. Essentially, undefined behavior, not good. So ideally, I would have populated this with, or initialized this with equals 0, but this way, if I do this conditional check, I'm guaranteeing that the width was found before I actually draw the string. And as we can see, it returns a 0 and success, and therefore all I need to do is if not, so meaning if it was successful, returning 0, so inverse of that, if 1, like if this is 1, then I have obtained the width and I can do the next thing. Now, as you can see from the documentation, it takes in the string that you want to check the length of, and in this case, it was just this one that we generated before with sprintf, and it is, you take in a pointer to the width and the pointer into the height. So these are the two variables where you want to have the return value stored in. So we don't want the height, so I've passed in null, because if I pass in null, essentially my function in the library will just do nothing for this variable. It won't actually get the height, but the width we want. And so I'm using the dereference ampersand to send in a pointer to our variable where we're going to store. So we have this width here. So this is the integer where the width will be stored. So after this returns and has given us our width, we can then go and draw it. Now we'll try and find, where is it? Get TUM draw text here. Print a string to the screen, blah, blah, blah. And so is printed to location X, Y. This location is referenced from the top left corner of the string's bounding box. And this bounding box size is exactly what we got from TUM get text size. So we need to pass it in the width, or the X value, and the Y value. And this is what this line is. So this is the string we want. And this is the X value, and this is the Y value, and the color. And so we got TUM blue, which if you look at what I showed you before, it's just the hex value that I found online for TUM's blue. Now, the X values, we want to put the string in the center, but if I was just to put screen width divided by 2, it would put the top left-hand corner of the string in the center of the screen. I mean, the string would probably be like it will go from the middle to the edge of the screen, which is not what we want. We want to then take it back half of its width into the middle, and so I have minus, and this is the width we found, divided by 2. So hopefully this makes sense. And then the same thing for the height, but instead of I could have gotten a variable, put it in there and found the height, but I know the font I'm using the default font, and there's also some macros or defines that give you these heights. So you don't necessarily need to do this. If you don't know where to find this, you can also just use the same process to get the height. And so after this, let's get called, I should have probably returned 0 on success. I should have probably done some error checking here to say, if successful, but really, to be fair, if this fails, what are we going to do? Like, exit our system. Maybe we got super lucky and something that backend happened. We can just draw the next frame, like crash exiting this. The program might be a bit too extreme. But maybe we could have printed an error message to the terminal or something with using printf, because it would print out, or using fprintf to print a standard error. We could have printed like, hey, this call failed, right? So we could have done another conditional error check there, but and then we essentially just call this update screen, and maybe, as I sort of explained it before, and so this executes all of the queued draw jobs. So each call to one of these like some draw functions creates a draw job, and then when you call this update screen, all of these jobs get written to the screen in sequential order that they were actually created. So this, if you read this, makes sense, right? And then we'll get to the last line of code, which is also terribly formatted. So we'll take him and put him up here. Format you about. So As I was explaining in the last lecture, there's two sort of very common delay functions, vtask delay and vtask delay until, and one of them being a absolute delay and one of them being a relative delay. So this vtask delay, it means it's just going to sleep from 1,000 ticks from the moment that this line of code gets run. It doesn't have any sort of reference start time or anything. So this basically is just going to get this code to run once per second. Now, if this code here takes more than a tick to run, which it probably doesn't in this case, but if it did, I would then be delaying, my entire loop would take over a second to execute, and since I'm updating the time every second, eventually, after 1,000 seconds or 1,000 ticks of running of my code, I would actually probably miss a second. Like it would say there's been 4 blah 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 since the epoch, and then there's been 6. And this is the problem of not using a relative time but using an absolute time, is that your frames can actually sort of have cascading effects that eventually they cause some sort of an error, right? But this is demo code, and I just want to show proof of concept. It's by no means good code. So that should hopefully explain this entire file. Things, for instance, like this at the bottom, these aren't necessarily needed. These are application hooks that are needed there by FreeRTOS's backend. So you shouldn't really need to use these as a sort of like advanced features of FreeRTOS that we won't cover in this course. Just leave them there. If you take them out, feel free to take them out and try and compile your code and see what happens, like read the errors and whatnot. But if you don't put them back in, you'll get these errors. I think that's pretty much about it. So I think I'll end this video there, and then I will do another video now going over the drawing libraries and stuff, looking at the masters main.c in a bit more depth. So thank you. I hope that this the microphone was okay. I'm just using my mic from my laptop, and that the screen recording's resolution was also understandable. So thanks, guys.